Hi, everybody. Welcome back. In our last video, we started talking about synaptic transmission and how neurons communicate with each other. In this video, we're going to take a little bit more in-depth look about how that communication occurs and about how how the action potential takes place. So just a quick little recap. If you remember from our last video, we talked about the upstream neuron sending messages to a downstream neuron. So our example, we had this particular neuron that we looked at. We said, okay, well, this neuron, these dendrites have a bunch of receptors on them, and these receptors will receive the neurotransmitter that has been released from an upstream neuron. Once this neuron receives enough stimulation, it has enough neurotransmitter that it's received, and it changes the charge of the inside of the cell, an action potential will fire. In other words, it sends its signal rushing down this axon down to the synaptic terminals. At the terminal of this cell, it's going to cause those vesicles to move to the edge of the membrane, merge with the membrane, and release the neurotransmitter into the synapse, which will then be picked up by the dendrites or receptors on the next neuron. So that was kind of a once over on what we talked about in our last video. So synaptic transmission, we have the synapse, the gap between the sending neuron and the receiving neuron. Remember the mechanisms of the synaptic transmission: synaptic vesicles at the end of the axon merge with the cell membrane, and that neurotransmitter is released into the synapse. The neurotransmitter that is released then binds to receptor sites on the dendrites of the downstream neuron, and this can lead to an action potential in that downstream neuron. Okay, let's take a quick look at what the cell membrane looks like. We talk about these receptors that are inside of the cell membrane, but it's kind of nice to know what the cell membrane looks like. So here is our cell membrane, and this is what you would call a lipid bilayer. We're not going to get into too much detail. I'm going to talk a little bit vaguely because this is an introductory course and not a biopsychology course. But basically, this lipid bilayer is what makes up the cellular membrane. This membrane is keeping the cytoplasm, which is the fluid inside of the cell, separate from the extracellular fluid, which is the fluid outside of the cell. So that's its main job, is to keep the inside of the cell separate from the outside of the cell. Embedded within this lipid bilayer in our cell membrane are these other types of proteins. This particular image here is a protein that is used for little molecules to travel back and forth across the membrane. So this would be a type of channel. We would call this a protein channel. This channel lets ions of different types pass through the cellular membrane, because these little molecules cannot get through this membrane. They need a channel of some sort to go through. So this particular channel looks like it is a potassium channel. K stands for potassium. And this is a little positively charged potassium ion. And when the membrane is at what we call a resting potential, so this is when it is not sending that signal down the axon, it is resting. It's at resting potential. And during that time, this little molecule of potassium can just drift back and forth through this type of protein. The reason for these little proteins to be able to passively allow certain things to go through is to keep the cell at homeostasis. So these little movements can keep the cell where it needs to be. The inside of the cell is more negatively charged than the outside of the cell. So interestingly, I mentioned in our previous video that we are creatures that are electrical. We are just kind of like living batteries that walk around. A battery uses things like potassium and magnesium and sodium in your regular battery. If you were to look up what's in a battery, those are things that are in a battery. If you look inside of our cells and in our cellular or extracellular fluid, you'll see those same things. These Na molecules, these are sodium chloride. This is sodium and chloride. They're bound together into sodium chloride. We have potassium. We also have magnesium, which you don't see. And these are all elements that you would see in a battery. These types of things, all of these little ions have charges, positive and negative charges. And it's the makeup of these ions inside the cell and outside of the cell that give you the net charge inside and outside. For example, in here we have inside of the cell, we have all of these large proteins. These are some very large types of proteins, and they are negatively charged. So they have very strong negatively charged things. We have some chloride inside, the chloride and some sodium chloride. The chloride is negatively charged. These potassiums in here are more positively charged, but they don't have as strong of a charge as these large proteins that you're seeing here that have the A on them there. So because of the makeup of all of these things inside of the cell, our inside of the cell is more negative than the outside of the cell. So when this cell is at rest, the inside charge of this cell would be about negative 70 nanovolts. I think they're nanovolts, and or millivolts, negative 70 millivolts. So that's how negative the charge is. The outside of the cell is not that negative. I don't know what the actual charge is outside, but it is not as negative. So it's a little closer to zero than this. On the outside here, we see that along the edges of the cell, we have a bunch of sodium, positively charged sodium ions kind of lined up along the edge of this cell here, along our membrane. On the inside, you see these giant negatively charged ions alongside the inside of the membrane. Now, if you've ever played with magnets, you will know that if you put two positive sides of the magnet together, they're going to resist one another and push apart. They will not click together. If you turn it around and you have one positive and one negative part of the magnet, they snap together really quickly. Well, that's what's happening along this cellular membrane. We have these large negative ions here, and on the outside, we have these positive ions. So these positive ions are attracted to these negative ones. So they're just kind of lining up outside the cell. And this is important because when we talk about an action potential, and we're talking about changes that happen within the cell, we talked about the net charge of the inside of the neuron becoming less negative. And the way it becomes less negative is because a lot of these sodium ions that are just hanging out real close to the edge, as soon as they get the opportunity to rush inside, they do that. So if they get a chance to go on to the inside, they rush in, and that extra influx of those positive ions creates a change in the net charge of the inside of that cell, making it more positive. When it becomes positive enough to a charge of about negative 55, so it goes from negative 70 to negative 55, that's the point when that cell can fire its signal down that axon. That's the point when that action potential can occur. So right here, we see that this is just kind of one of those proteins that is a channel that things can move through. But there are also things in this cell membrane called voltage-gated channels. So what happens when the action potential occurs and when the neuron is stimulated, a channel like this opens, a channel that is normally closed. So we would have a channel like this, but instead of letting potassium just passively float through, it would be locked tight. And it would be locked tight until you get the correct voltage. When we get the correct voltage, then this will open up and a surge, this is called a sodium gate, it would be called a sodium gated channel, voltage gated sodium channel. The voltage opens it. It reaches that voltage of negative 55. All of this sodium that's just hanging out here along the edge rushes into the cell, and then it depolarizes or changes this section of the cell. So this little edge of the membrane becomes more positive. So our action potential is really hard to explain without having a board, but I'm going to do the best I can. So the way this works is, remember, we have our dendrites that end up getting stimulated. So each time the neurotransmitter binds to one of those little receptors, that little area of the cell becomes depolarized. It becomes less negative on the inside. So that little area becomes just a tiny bit more positive. When that happens enough to where the whole inside of the cell reaches the negative 55 millivolts, so we got all those tiny little stimulations. When it finally gets to that point, the cell fires like a trigger. Boom, sends that signal right down the axon. That signal starts from where the cell body joins the axon. So right in that spot where the cell body joins the axon, that's where it takes off. And what we would see all the way down the axon, this is not that great of a image. Don't really like it, to be honest. We'll go back and just look at our neuron. So all of this has been stimulated to where the inside of the cell finally, those little channels are opening, and sodium's flowing in, and the voltage of this body of this neuron is no longer negative 70. It has become more positive and is now up to negative 55. At that point, an action potential zips down the axon. And that starts from where this cell body joins the axon, at the axon hillock. And I think there's a new term they use for that too. But basically what you need to know is it starts right where the axon joins the cell body. Now, we kind of know, okay, this changed, but how does this action potential propagate its way down the axon? Well, the way that this happens is kind of like a wave. If you've ever been at a stadium or in a, maybe at school in the auditorium where you do a wave, where like you're waiting, the wave is coming, and the person next to you stands up and does their wave, and then as they sit down, you stand up and do your wave, and the next person next to you, as you're sitting down, they stand up, and it goes all the way down. That is how the action potential propagates. The little voltage-gated sodium channels on the axon kind of take turns all the way down the axon. So they take turns all the way down the axon, just like a wave. When the first one up here opens, it'll open, and then the sodium rushes in and some potassium rushes out and some other things happen. Some of these fluids all exchange. But as soon as that happens, this tiny little area of the cellular membrane depolarizes. That means it becomes less negative. It becomes more positive. So that little voltage-gated channel is standing up. That's the one standing up, right? And then as that starts to close, the next one is standing up. So this one opens, And then right as it starts to close, the next one down the line opens, and then this one starts to close, and the next one down the line opens, and the next one starts to close. So it goes all the way down. So we have this one open and close, and as this one's closing, the next one opens. So just like a wave. Hopefully that makes sense to you guys. It's hard to do not in class. So as the person next to me is standing, okay, so I am the voltage gated channel that just stood and was open, and now I just sat down. The little voltage gated channel next to me is standing up and doing their part of the wave. While they're standing up, I am already starting to try to recover from that. I am trying to get back to that -70. I'm trying to get back to that resting potential. So I have opened up different channels that I have opened, kind of like I had the sodium channel open. There's something called a sodium potassium pump that goes into action, and some other mechanisms happen to where the fluid exchange can get everything back to normal. So as soon as I get back to my seat as the little neuron, as the little voltage gated channel, then other things are going to start happening to try to bring that section, that little tiny section of the axon back to its normal voltage. So as this part is going back to its normal voltage, this one here is changing to be more negative. So it just takes place all the way down like a wave. I really hope that makes sense. Okay, so I'm going to go back to so back to this graph. So this is what, this is a depiction of a neuron for the action potential here. And what's happening during this action potential is that we have sodium ions rushing in. Remember, those are the more powerful, the more positive ones. Those sodium ions are rushing in, and some of the other ions are drifting out of the cell. Well, potassium ion, as soon as this is done, so basically, remember, the open phase there where the action potential is happening right in that spot on the axon, in that very spot, as soon as the action potential passes that spot, a bunch of potassium flows out of the cell. Remember, that's a positive ion. So those positive potassium ions, these guys rush out of the cell as much as possible. Like they just go flying out, pshoof, to try to bring that cell back to homeostasis, which would be that -70 millivolts. So they're trying to recover from -55 millivolts to get back to -70 millivolts. So a ton of these positively charged potassium ions zip right on out of the cell. And remember, we have these channels that are allowing them to do that. So here's how that looks on a graph. So we're going along before the neuron sends its signal or sends its action potential. We have between this -70 and this -55 right here, this is resting potential. We have these changes occurring along the cellular membrane that are just starting to change the charge of that neuron. As soon as that neuron reaches -55, we call that a threshold potential. It has reached the threshold. Once it reaches the threshold, that's the point where the trigger is pulled. The trigger is pulled and that action potential is fired. At that point, that particular area of the axon is completely depolarized. There's way depolarized back to about positive 40 millivolts. So it goes completely from a negative charge to a really positive charge. Because remember, that sodium, that voltage gated sodium pump there opens up. And it pumps all that sodium in, which are all those positive ions, dump into the cell during this period, bringing the voltage all the way up to positive 40. Then at that point, This is when remember we're talking about the standing part. This is the standing part right here, where all that positive ions are dumping into the cell. Then repolarization occurs. This is when you're sitting down. So as you're sitting down, as this part of the membrane of the axon is trying to recover, that's when all of this potassium starts to flow out. So all these positive ions start flowing out. There's something called a sodium potassium pump that starts pumping. There's all sorts of things that occur. So as this cellular membrane on the axon where the action potential has just passed, as it's recovering, it actually gets to a point where it's way more negative, or a little bit more negative than it was to begin with. So instead of just stopping at -70, it actually, too many of those potassium ions probably flow out. Maybe a few too many sodium ions flow out of the cell, creating it to be even more negative than before it started. During that period of time, when the cellular membrane is trying to recover and it has gotten to a point where it is even more negative, another action potential cannot occur during that phase. So that's called a refractory period. So this is what it looks like graphically. All right. Some more terminology. Synaptic transmission, the resting potential. Axonal conduction, transmission of a neural impulse along the length of the neuron. Resting potential, electrical charge of a neuron when not firing a neural impulse. And that's what we were talking about. It's about -55, whereas when it is having an action potential, we're talking about -70 millivolts. The action potential is a change in the electrical charge across the axonal membrane. It operates on an all or none basis. So basically, what that means is you don't have like half an action potential or a weak action potential. The cell either fires or not. Just like if you were firing a gun, you're either pulling the trigger and it shoots, or you're not pulling the trigger and it doesn't shoot. And it's going to shoot the same every time. It doesn't matter how hard you pull the trigger, it's going to shoot the same every time. What you can have that is a difference in the action potential or in the synaptic transmission is that you can have a cell that maybe fires more rapidly because it's got more got more of a stimulating effect going on with it. So it's got either, a lot of neurotransmitter that is being dumped into the synapse, so the cell is able to fire multiple times. So the rate of firing can change, and but the strength of the signal does not change. All right, some more terminology. Action potential. Neurotransmitters from nearby neurons attach to receptors on dendrites, causing the membrane potential to change. And remember, the membrane potential is when we're talking about that voltage. So it's having the voltage change. Depolarization of the membrane potential becomes less negative, making the neuron more likely to fire. That is also called excitation. Hyperpolarization, that's when the membrane potential becomes more negative, making the neuron less likely to fire. So that is inhibitory. Or inhibition. If the level of charge reaches the threshold of excitation, which in this case we're talking about being that -55 millivolt, an action potential will occur. Ion channels open, causing that sodium to rush into the cell and the inside to momentarily become more positive. So threshold of excitation is the level of change in the membrane that causes the neuron to become active. And action potential is that signal that's being sent down the axon. Okay, all right. And okay, so I think I'm going to go ahead and stop here since this was kind of a long one. And then we'll talk a little bit about neurotransmitters and drug effects in our next video. And then we'll probably go ahead and talk about brain imaging as well in that video. I think that will do it for us today. Let me know if you have any questions as usual. And you guys take care and have a good day. Bye-bye.